In this video, we're going to be performing basic operations with Pymol. The first thing we're going to do is we're going to head over to rcsb.org and download a protein data file so that we can play around with it. Once here in this website, we can type the name of the protein we want to search for. In this case, myoglobin. And look at all the variations they have and select one, or we can, if we know the name, we can just input the code and go directly to the protein we want. Here we can look at the details of the protein and the publication related to it. From here we can download the file in PDB format. Once that is done, we can go to Pymol, go to Files, Open, go to our download folder, and select the protein data file. That's it. Another way to do this, if we close here, is to simply type in the terminal fetch and the name of the PDB data file. And then it opens automatically. Now, once the protein is open, the protein data file is open, we can proceed to edit it as we want. Now, we have our protein and we can explore it. But there's some information missing, like the sequence. If we wanted to see the sequence, we can just play around here. And we can go directly to display and then select the word sequence. Then we can see the one-letter code for the amino acid sequence on the protein, as well as interesting parts of the protein like the heme group in this case, the oxygen ligand, and some salts and other things. As you can see in this file, there are many oxygen atoms scattered around the PDB file. Those oxygen atoms correspond to water molecules. But missing, you will find that the hydrogen atoms are. There are no hydrogen atoms in this structure. So if you wanted to, we could add those atoms in a later step. But for now, we're gonna leave it like that. And then I'm just going to change from the one-letter code in the amino acid to three-letter code or residue name. This way I can better understand what I'm looking at, as well as see the numbers the amino acids correspond to in the sequence. Okay, let's say we wanted to create a representation of the heme group. I can select the heme group in two ways. I can either click it here and then the heme group is selected, as you can see in this tiny green line in the sequence. Or I can go directly to the sequence and press on it, and then the heme group is selected. At the same time, there will be a selection or cell icon generated here. I can rename that icon to whatever name I want so that it's saved, so that selection is saved. I'm just going to clear that up and write heme for the name of that selection. Now I can proceed and change or edit that selection as I want to, or just keep it there saved because it is an important part of the protein. Now, if we wanted to know or highlight parts that are important around the cofactor or around the active site, we can simply use a tricky or very useful command in Pymol, which is, I'm gonna paste it here. You can use this and edit it as you want. And what the command says is show sticks or turn into sticks by residues everything that is at 5 angstroms from the selection, whatever selection I make. In this case, my selection is going to be the heme group. So I'm just going to change this for heme and press enter. So there I can see all the amino acids or all the amino residues that are about 5 angstroms from the heme group that might be important for the function of the protein. And from there I can proceed and explore a bit more. I can zoom in, look at them, identify them in the sequence by pressing on them, creating a new selection, etc., etc. Now, let's say you wanted to change how the oxygen molecule looks in this representation. We can just select it, click on it either here or in the sequence, and then go to the selection, right? We're just gonna change that name again. We're just gonna type, erase this, and type O2. Press enter, we rename that selection. And now we're gonna go to the letter S or show, and we're gonna show it as sticks also. That way it's easier to visualize. As you can see, when I rotate the representation, the heme group is not at the center. It kind of tilts on its side. So I'm going to select the heme group representation here, the selection, and press the button A for action, and then I'm going to press center to center the representation right at it. That way, when I move the screen, the heme group will always be at the center. Now, let's say we wanted to make a measurement of how far the iron atom is from this first oxygen atom in this oxygen molecule. For that, I will use a very nice tool. In the terminal, I'm going to go here to the UI or the user interface, and I'm going to go to Wizard, Measurement, and now we're going to get this tiny box on the right hand side that will allow us to measure distances. And I'm going to press the word distances, measure mode, distance. And now here I can just press on the iron atom and on the closest oxygen molecule. Oops, I pressed something else. Iron atom, the closest oxygen molecule. There, we can now see the measurement in angstroms, or the distance in angstroms from the iron to the first oxygen atom. If we wanted to make another measurement, we can just click on another atom and then on a secondary atom, we would get another measurement. In this case, from the second oxygen in that oxygen molecule to the nitrogen in histidine 64. And we can get another measurement in units of angstroms. Finally, if we wanted to save this or make a representation, we can just go to the terminal, and here I would recommend changing the background, which would be good. We can just go to display, background, and then change the color of the background. You could do white if you wanted to print on paper, or put it in a PowerPoint presentation where the background is white, or we could just leave it black if we are like in a video like we are now. And then we can proceed to save it. So file, we can save the session, which includes everything we've done up till now, or we can export the image as a PNG image file. On the other hand, if we wanted to make a mutation or a change in the sequence of amino acids in the protein, there are many ways to do it, but one of the easiest ways to do it is to go to charmgui.org. Here, you can create your own account with your institutional email, just for educational purposes. And then we can go into input generator. We're just gonna sign up. I'm gonna enter my credentials there. And there I can go to PDB reader or manipulator. And I can go down here and input the name of the PDB that I want to use, which is the same one we already used. Here, the reader automatically separates the PDB into all its components. Here we have salts, we have the oxygen ligand, we have the heme group, and because I didn't modify the original PDB, I'm just going to select everything so that the new PDB contains everything too. But if you wanted to eliminate something, this would be the step to do it. Just don't select. Once it's done, here we can alter a few things in the system, like the pH, the name of the ligand, how is it going to be represented. But for now, I'm only interested in showing you how to mutate certain parts of the amino acid sequence. Here it's important to specify how the protein is going to be coordinated to the active site, which is the heme group. I'm just gonna make sure it's histidine 97. And I want to perform a mutation. So I'm gonna press this check mark here. And let's mutate one of those important amino acids that we saw at 5 angstroms from the active site. And one of them was histidine 64. So I'm just going to select the number 64 here, the number of the residue, and here the name of the residue, which is histidine. Charm GUI is very smart, so if you select 64, it will probably select the right name of the amino acid. And then I'm going to select the alternate amino acid, the one I want to put in instead of the one that is in there already. So I'm going to add, let's see, phenylalanine. We can make a really big change with this in the activity of the heme group, so it's a radical change. If we wanted to add more mutations at different parts of the change, we just click here, the add mutation, select whatever we want. But one is good for now. After that, just press next step, generate PDB. Now that the PDB has been generated, we have a whole bunch of files here that we can download on a zip file. But the important file is going to be this one right here, charm PDB. That allows us to view the structure. So we can download that. Now, I'm just going to open the new PDB file with Pymol. The file, open. Now it's on my desktop. And open the new PDB file. They seem to be overlaid, but they're not aligned at all. So the alignment would be a computation that we can perform later. But now we do have a mess of the water molecules, right? There's a lot of water molecules for both representation. So I'm just gonna proceed and delete the water molecules from the representation in both of them. I'm gonna go here to this selection here that says type 1 PDB reader, and I'm just gonna remove the waters from there. And then I'm going to go to the original structure, protein, and remove the waters from that, so we don't have those pesky dots all around. Now they're overlaid, but they're not aligned. We can do that in a second, but for now I'm just going to create the same representations as I had for the original one. I'm going to go in the second sequence to heme, and I'm going to rename that action. I'm going to rename selection as heme2, and I'm going to select the oxygen from the second structure, right, oxy, and I'm going to rename that to O22. Actually, I did that wrong. I did a 0, it's an O. O22, okay. And I'm gonna change that into sticks also. Show as sticks. So now I can proceed to align both structures so that we can actually compare them actually compare both sequences. And I'm just going to type in the terminal align, and then the name of the first PDB that serves as a reference, comma, then a space, and then the name of the other PDB that we are aligning. Underscore. And then we're going to press enter. Now, both structures are aligned, and we get an RMSD value that tells us how well aligned they are. So the closest to 0 the RMSD is, the better our alignment is. So now that they're perfectly aligned, we can go ahead and look at the sequence like we did before using the command. I'm just going to copy here the command again to get those important amino acids around the active site. I'm going to paste it here. This time I'm just going to do 4. And I'm going to say heme, selection heme. And it says small form selection because I didn't select the selection. And now we can go again off heme, right? There we go. But I did the same thing. I did it on 5. That's not a problem. And I'm going to do the same thing for the other selection. For the other, the mutated protein. I'm going to paste the same command. And then type the selection name heme2. There we go. Now we can zoom in. We can zoom in with the right click button. And we can compare a little bit the active sites. We can see that one now has something weird on position 64, and then we have all these white spikes, which are actually hydrogen atoms. So the process that we did on Charm-GUI added the hydrogen atoms to the structure, to the whole protein. And here we have something a bit weird, but it's just amino acid number 64 in the mutated form, right? We have the phenylalanine right on top of the representation of the histidine. So we have to play around a little bit with that. But for now, we're gonna leave the tutorial here. These are just the basic operations. If you don't like the representation, you can just change them, right? You can change the style, the representation, the color, the background, and everything else. I hope the video helps a little bit and that you enjoy it.